All right, good day. Thank you for joining the session for nuclear chemistry part 2. So this is the one that will be posted later on in the day. So I'm going to just give you a short summary of radioactive decay. Now we first have beta particle or electron production. As you can see here in our example, we have the same mass number. Remember, this is the mass number. And there is a change in atomic number. So the change in atomic number is always +1, and the neutron to proton ratio actually decreases. So we have first actinium 227 changes to thorium 227 and injects an electron. Next, we have a positron production. Again, it is the antiparticle of the electron. So it also does not involve a change in mass number, but there is definitely a change in the atomic number. So this time it's -1. So you have here nitrogen 13. It becomes carbon 13 through the ejection of a positron. Now you have electron capture. So basically, um, excuse me, the electron is on the reactant side. There is no change in mass number, and there is a change in atomic number. So it's -1. So you have acetine 73. Once you have electron capture on your reactant side, becomes GE. So what is GE on the periodic table? Let's look. That is germanium. Okay. All right. Now we also have alpha particle production where you have a change in mass number. It's -4 and a change in atomic number. So this loses two neutrons and two protons. This one loses two protons, right? So you have 210 polonium becomes lead 206. And remember, an alpha particle is basically a helium nucleus. You have a gamma ray production, which there's no change in mass number, no change in atomic number. So you have an excited nucleus. Turns to ground state nucleus plus gamma ray. You also have spontaneous fission, wherein there is no change. So you have californium turning into lighter nuclides and neutrons. Okay, so we have something called a decay series, which is when a radioactive nucleus cannot reach a stable state through a single decay process, right? That's why it's called a series. It continually is in radioactive decay. So what happens is that you have a parent isotope that's radioactive and turns into a daughter isotope. Right? And then if the daughter isotope is still radioactive, it goes through a succession of radioactive decay until you have a stable nuclide. Okay, so in this one, we have the decay series from uranium 238 to lead 206. So the radioactive nuclides decay from uranium 238, so it goes through alpha particle production, thorium 234 goes through beta particle production again, and then it goes to alpha particle, then beta, alpha, beta, then alpha production until it becomes lead 206, which is a stable nuclide. So that's how radioactive elements sort of go through radioactive decay until it becomes stable, right? And we have another decay series from thorium 232 to lead 208. So it undergoes a series of decays as well. Okay, so this is just another summary of radioactive decay. You can see this in your PowerPoint that I will post. Okay, so let's talk about the kinetics of radioactive decay. So we've tackled chemical kinetics before. So luckily, we have here already the formula for radioactive decay. And notice how the rate of decay is equal to Kn, right? K and N. So that means This is very similar to the first order rate law. Okay, so the rate of decay is actually first order, right? So this is your integrated rate law of radioactive decay, where an N naught represents the original number of nuclides at t is equal to 0, and N represents the number remaining at time t. Okay, and you also have the half-life. Again, this is for a first order reaction. Okay, so we have here this problem. Technetium 99M is used to form pictures of internal organs in the body and is often used to assess heart damage. The M for this nuclide indicates an excited nuclear state that decays to the ground state by gamma emission. The rate constant for decay of technetium 99M is known to be 1.16 times 10 raised to negative 1. Sorry, this is negative 1 per hour. What is the half-life of this nuclide? Now, let me just change this just to correct it immediately. Okay, so what's the half-life of this nuclide? Okay, so we're already given the formula for half-life. T1 half is ln2 over k, or 0.693 over k. And so what is k? K is 1.16 times 10 raised to negative 1 per hour. So just do the same thing. ln2, or 0.693, divided by 1.16 times 10 raised to negative 1 over h. So that gives us 5.98 hours. Okay, so it takes up 5.98 hours for a given sample of technetium to decrease to half the original number of nuclides. All right. So let's go to kinetics of nuclear decay too. So now we're going to focus on half-lives and how much things are reduced with half-life. Okay, so the half-life of molybdenum is 66 hours. How much of a 1,000 milligram sample of, oh, so what this means here is, let me just refine it, it's 99 molybdenum, okay, is left after 330 hours, okay? So your time here is 330 hours. How much of a 1 milligram sample of molybdenum is that? Okay? So one way to solve it is that to recognize that 330 hours represents 5 half-lives for 99, for molybdenum 99. Okay? So you sketch this, right? Okay. So we have 1.000 milligrams. Okay, after 66 hours, that is your time in hours. After 66, this one is 0.5 milligrams because it's your half-life. Okay, so that's after one half-life. And it goes below. Again, yung agwat is 66. 2, 3. Wait, let me just slope it down a little more. 6. Okay, that is after 3 half-lives. 4. This is 5. 66. So this becomes 0.250, 0.125, 0.062 milligrams, and 0.031 milligrams. Right. And remember, 330 hours divided by 666 hours is equal to 5. So after 5 half-lives, what you have. This one has the um, molybdenum, 99 left, is equal to 0.031 mg. Right. Let's talk about nuclear transformations. Okay, so in 1919, Lord Rutherford observed the first nuclear transformation where one element is changed into another. So we have here um, nitrogen 14 was bombarded with a helium nucleus. And what again is a helium nucleus? This is an alpha particle. It gets bombarded with a helium nucleus and it turns into oxygen 17. And what emits is hydrogen. Okay, and then you have your oxygen 17. All right, so this isn't the only time that it was that it occurred. So 14 years later, Irene Curie and Frederick Joliot, Irene Frederick Joliot, her husband, observed a similar transformation from aluminum to phosphorus. So we have aluminum 27. Again, you have a helium nucleus. This is an alpha particle. So it was bombarded again with alpha particles, producing phosphorus 30 and a neutron. So a neutron was ejected, right? So many other nuclear transformations have been achieved using something called a particle accelerator. Okay, so this is one way of how scientists discover new elements. Like before in the early 2000s, all right, the the periodic table actually wasn't filled up yet. You know, we knew that the other elements were going to be discovered, but we just didn't know when they were going to be discovered. So you'd see gaps in the periodic table. You would see, okay, this is element what? 118 wasn't discovered yet. Oganesson wasn't there. Tennessine, right? Nihonium, it wasn't there. All right, so these elements have been discovered fairly recently. So, how did the scientists discover these new elements? Well, the scientists use particle accelerators. So, they give particles, or rather, they shoot particles at very high velocities. So, you have a target nucleus, okay, and a positive ion, which experiences electrostatic repulsion, right? Because the nucleus itself is full of protons and neutrons. And so, of course, when you have a positive ion, this will repel because they're of the same thing. Now, how do you make them collide with each other and actually react? You actually accelerate the particle to a high velocity, which overcomes the repulsion and penetrates the target nucleus. Okay, so you have this machine. It's called a cyclotron, which is a type of particle accelerator. Okay, this is the cyclotron at Triumph. This is Canada's National Laboratory of Particle and Nuclear Physics. And how this actually ejects particles is you have your ions introduced at the center. This is your ion source. And then this is pulled back and forth by the D-shaped electrodes by constant reversals of the magnetic field. Okay, so when you constantly reverse the magnetic field for positive, negative, it's going to be pulled back and forth. Because of that, the particle velocity increases, and when the particle has sufficient speed, it exits the accelerator and is directed at the target nucleus. Okay, so you have your linear accelerator, which changes the electrical field to accelerate a positive ion along a linear path. So as the ion leaves the source, these odd number tubes are negatively charged. And then the even number tubes are positively charged. So the positive ion is attracted into tube 1. And then as the ion leaves tube 1, the tube polarities are actually reversed. Tube 1 is positive, which repels the positive ion. And then tube 2 is negative, which attracts the positive ion. So this process continues, which also produces a high particle velocity. Now we have your neutron here, which is used as bombarding particles to cause nuclear transformations, right? Your neutron is uncharged and they're not repelled electrostatically by a target nucleus, so this makes it perfect for bombarding. So it's not unrepelled and it's readily absorbed by many nuclei. So this one actually leads to new nuclides, and the fission reactors are actually the most common source of neutrons. So this is your CERN, Large Hadron Collider. So this is the world's largest and highest energy particle accelerator, and it's built by the European Organization for Nuclear Research. So it's at the border between Geneva, it's in Geneva, Switzerland. It's basically at the France Switzerland border, if I'm not mistaken. So it allows a physicist to test the predictions of different theories of particle physics. So uh, you can read up on this. So this has a lot of applications. So one thing about these particle accelerators is that they also led to the discovery of neptunium. So by using neutron and positive ion bombardment, scientists have been able to fill in the gaps of the periodic table. So prior to 1940, the heaviest known element was actually uranium. But what happened is that when you bombard uranium with a neutron, it becomes uranium 239 and then it decays. It goes through radioactive decay. Okay. And look at that. You have neptunium and a beta particle, right? Neptunium was produced by the neutron bombardment of uranium 238. So, in the years since 1940, the elements with atomic numbers that are greater than 92 are called the transuranium elements, right? They're beyond uranium and they have been synthesized. And notice how a lot of these elements actually have very short half lives, right? You have neptunium, which only lasts for what? 2.36 days, right? It immediately degrades, okay? Plutonium, half life is pretty long, 24,110 years, right? Americium, 433 years, pretty long. Curium, also short half life, 163 days. And notice for Californium, it's only 45 minutes. So, uh, one reason why these elements were not discovered yet is because look at their half lives. They're gone within what? Within less than 2 hours, especially for California. So these are elements with atomic numbers greater than 92, and they have very short half-lives, and only a few atoms of some have ever been formed. And the chemical characterization of these elements is actually difficult due to their half-lives. Okay, imagine trying to analyze a sample that's going to run out within 2 hours. You don't even have the sample prep. So it's very difficult to really show or investigate how these chemicals react because they disappear immediately. So we have the detection and uses of radioactivity. We briefly touched on this in the first part. Okay, so you have something called the Geiger Mueller counter, also known as a Geiger counter or survey meter, which measures radioactivity levels. So the high energy particles from radioactive decay processes produce ions when they travel through matter. So the probe of the Geiger counter is actually filled with argon gas. Remember that argon is a noble gas, so generally it's unreactive. However, in this case, in the Geiger counter, it's ionized by a rapidly moving particle. So you have argon, which is generally underreactive. It gets ionized by a very high energy particle and it emits electrons, right? So normally a sample of argon wouldn't conduct a current when an electrical potential is applied. However, when the high energy particle allows a momentary current to flow, there is a formation of ions and electrons. And the electronic devices actually measure this current flow. And the number of these events can be counted, and a decay of the radioactive sample can be determined. So you have something called a scintillation counter. Okay, you might see the same terminology actually be used in medicine. So the scintillation counter detects levels of radioactivity. So zinc sulfide and other substances actually give off light when they're struck by high energy radiation. Okay, I have something called incident particle and a scintillator. And a photocell senses the flashes of light that occurs at the radiation strikes and then measures the number of decay events per unit time. Okay, now let's get into a bit of history. So, how do we know how old things are? Okay, so one of the reasons that is in development is carbon 14 dating. So this was originated in the 1940s by Willard Libby, who's an American chemist who received a Nobel Prize for efforts in this field because it allowed us to calculate how old or how basically the age of certain things, of certain substances. So pictured here is a Brigham Young researcher, Scott Woodward, for taking a bone sample for carbon 14 dating at an archaeological site in Egypt. So in radiocarbon dating, it's based on the radioactivity of the nuclide carbon 14, which decays via beta particle production. Okay, so carbon 14 is continuously produced in the atmosphere. Okay, where high energy neutrons from space collide with nitrogen 14. Okay, so it's continually produced in the atmosphere, and this is based on the assumption that the carbon 14 levels in the atmosphere are relatively the same. So we also do this for wood and clothing artifacts, right? So it's used to date wood and cloth artifacts, and carbon 14 reacts with oxygen to form carbon dioxide. So a living plant has the same carbon 14 to carbon 12 ratio in its molecules as the same in the atmosphere because of the continual uptake of carbon. However, okay, if you cut the plant, if you harvest flaxseed, if you basically cut the tree, the the ratio between carbon 14 and carbon 12 actually decreases because of the radioactive decay of carbon 14. So because of the radioactive decay of carbon 14 and because of the ratio of carbon 14 to carbon 12, we are able to get a picture of just how old something is based on its decay. Okay, right? So this one, this is dendrochronologist Dr. Thomas Sweatham at the University of Arizona in Tucson. So they use data from collected long-lived trees such as bristlecone pines and sequoias, and what they're trying to fix now is that they're trying to find correction factors because sometimes the dates in the 20,000 to 30,000 year range have errors as large as 3,000 years because they're surmising that the carbon 14 dates over this period, 20,000 to 3,000 years ago, is very different. Okay, the ratio is very different from the ratios we use now. So they're trying to recalibrate. Okay, so the downsides of radiocarbon dating is that you have to actually destroy your sample. So the several grams of the object has to be burned to form carbon dioxide, and then use that carbon dioxide sample to be analyzed for radioactivity. There's another method that can use that. Well, you still have to take a bit of your sample and use it for 10. Use like 0.0001 grams, right? One, two, three. Yeah, that's correct. And you use a mass spectrometer. It's more accurate that way. Okay. Now let's talk about carbon 14 dating. How do you determine this? So the remnants of an ancient fire in a cave in Africa showed a carbon 14 decay rate of 3.1 counts per minute per gram of carbon. Assuming that the decay rate of carbon in freshly cut wood, corrected for changes in the carbon 14 content of the atmosphere, is 13.6 counts per minute per gram of carbon. Calculate the age of the remnants. The half-life T1 half is 5,730 years. Okay, so we have to remember our rate law, which is Kn. Okay, and then we have this one. We get the ratio ln n over no, right, is equal to, just to make sure that this is the correct formula, ln over 2 is equal to negative kT, right? It's first order reaction. So what we're going to do is find the ratio here. So we have rate at time t, rate at t equals 0. So rate at time t is actually 3.1 counts per minute gram and 13.6 counts per minute gram. Okay. All right. And so what we get for that value, K N or N O, right? And you cancel this out is 0.23. Okay. So we plug that value in. We use that integrated rate law. So it becomes ln ln 0.23 is equal to negative kt, right? And then how do we get k? Right, so this is missing. We use it from the half-life formula. T1 half is equal to ln2 over k. So we just substitute that. K is equal to ln2 over T1 half, okay, which is equivalent to ln2 over 5/730 years. Okay, and then we just input all of that into the same formula. So you have ln 0.23 is equal to negative 0.693 or ln2 over 5,730 years by t, right? And when you solve for t, you get 12,000 years. So the campfire in the cave occurred about 12,000 years ago. Hey, you have something here as well. How do geologists date rocks? So you also use radioactivity based on radioactive decay. So they use the ratio of lead-206 and uranium-238 to determine the age of the rock. So to determine the date of very old rocks, such as the ones 4.3 billion years ago, they use lutetium-176 and hafnium-176. Okay. So a rock containing uranium-238 was and lead-206 was examined to determine its approximate age. Analysis showed the ratio of lead to uranium atoms to be 0.115. Assuming that no lead was originally present, that all the lead-206 formed over the years has remained in the rock, and that the number of nuclides in the intermediate stages of decay between uranium and 206 calculate the age of the rock. Okay. The half-life of uranium-238 is 4.5 times 10 raised to 9 years. Okay. So we solve this formula. So we use the integrated first order rate law again. So again, to find K, you have T1 half is equal to 0.693 over K. Okay? And then you basically switch that. So you know the half-life. So you have ln n over n naught is equal to kt, which is negative 0.693 over the half-life, which was given 4.5 times 10 raised to 9 years. Let's do. Okay, so then we have to look for n over n naught. Okay, so that's what happens. So n over n naught represents the ratio of uranium-238 atoms now found in the rock to the number present when the rock was formed. So we're assuming that each lead-206 nuclide present must have come from the decay of a uranium-238 atom. So the originally present 238 atoms is equal to the number of lead-206 plus the number of uranium-238, because not all of the uranium-238 degrades into lead-206. So the ratio should be 0.115 because that was given earlier. So the ratio of 206 of lead-206 and uranium was given earlier, 0.115. Now what do we do with this info? Now, if we have this info, okay, we have the ratio of N and N naught is equal to uranium 238 plus lead. It's equal to 1000 divided by 1115. Okay, why 1115? Because it's 1000 plus 115. Okay, so that's why. And it becomes 0.8969. Okay, so it becomes ln n over n naught is actually ln 0.8969 is equal to negative 0.693 4.5 times 10 raised to 9 is equal to T. And so T is equal to 7.1 times 10 raised to 8 years. So this is the approximate age for the rock, and it was formed sometime in the Cambrian period. Now, we've touched on this briefly, the medical applications of radioactivity. So, radio tracers are radioactive nuclides that can be introduced in organisms and food or drugs, and the pathways can be traced by monitoring their radioactivity. So, you incorporate nuclides such as carbon 14 and phosphorus 32 into nutrients, and what happened is that it has produced important information about metabolic pathways. So you have iodine 131. It's actually used in the diagnosis and treatment of illnesses in the thyroid gland. So the patients drink a solution containing small amounts of sodium iodine 131, and the uptake of the iodine in the thyroid gland is actually monitored with a scanner. The same thing happens with thallium 201, and it's used to assess the damage to the heart muscle. Technetium 99M is also taken up by normal heart tissue and is used for damage assessment. So here are different radioactive nuclides with half-lives and medical applications for radio tracers. So we've seen here iodine 131. We have here for molybdenum 99, which studies the metabolism. Phosphorus 32 studies the eyes, liver, and tumors. Okay, so we have strontium, which studies the bones. Why? Because it's chemically similar to calcium. Okay, so these provide sensitive and non-invasive methods. So if you want to study what exactly happens in your patient's eyes, nose, red blood cells, tumors, you would opt for radio tracers, because instead of costly surgery where you'd have to sedate them under general anesthesia, this is a lot cheaper, and it gives a lot of information already. So it learn with these radio tracers, you learn about biological systems, disease detection, monitoring the action and effectiveness of drugs, and for early detection of pregnancy. Now let's briefly touch on the thermodynamic stability of the nucleus. So how can we calculate this thermodynamic stability of a nucleus, right? Because you have radioactive nuclei that degrade. Okay, we've touched on radioactive decay. So we can calculate the change in potential energy that would occur if that nucleus were formed from its constituent protons and neutrons. So this has a hypothetical process of forming oxygen 16 from 8 neutrons and 8 protons. So you have 8 neutrons here, and you bombard 8 protons, basically 8 hydrogen atoms, to produce oxygen. Right. And so the energy change associated with this process can be calculated by comparing the sum of the masses of the 8 protons and the 8 neutrons with that of the oxygen nucleus. So what do we have here? We have the mass of the total. So you have 8 neutrons, and then you place in the mass of the neutron, which is 1.67 times 10 raised to negative 24. You have 8 protons, and then you place in the mass of the proton, which is 1.67262 times 10 raised to negative 24. And you basically take the mass, and this will be the mass of your nucleus. Now, you have to use Avogadro's formula, so you have the mass of the nucleus, right? And use Avogadro's formula to calculate the number of nuclei per mole. And you'll get the mass, basically the molar mass of the nucleus. So 0.1366 grams of mass would be lost if we lose 1 mole of oxygen-16. So why is there a difference in mass? And how can you use this information to calculate the energy change that accompanies this process? So Einstein is famous for his theory of relativity, which showed that energy can be considered as a form of matter. So you have C representing the speed of light, which is 3.0 times 10 raised to 8 meters per second. And you have your energy change, wherein it's basically just showing delta E is equal to mc squared. Now, we can use this formula in the nuclear binding energy. Now, for binding energy is the amount of energy to actually break up a nucleus. So let's calculate the change in energy if 1 mole of oxygen-16 was formed from its neutrons and protons. So it's delta E is equal to mc squared. And you have same thing, you have the change in m, right? So E is equal to mc squared. So you have negative 1.366 grams per mole. That's your mass. C squared is 3.00 times 10 raised to 8 meters per second squared. And you have 1.23, negative 1.23 times 10 raised to 13 joules per mole. So notice how it's negative. So that means the process is exothermic. Okay. Now we also have something called the energy change for nuclear processes, right? So the energy changes for nuclear processes are extremely large with those observed for chemical and physical changes just because of how reactive they are, right? Nuclear processes actually constitute a potentially valuable energy resource, and the thermodynamic stability is actually represented as energy released per nucleon. Right. So for the energy change for nuclear processes, it's extremely large with those compared with those observed for chemical and physical changes just because of the amount of energy it releases. So these nuclear processes constitute a potentially valuable energy resource, and thermodynamic stability is actually represented as energy released per nucleon. Okay, so you have the energy released per nucleus, which we obtained here, negative 1.23. And just so that we can check the energy released per nucleus, so we divided by the Avogadro's number, so it's negative 204 times 10 raised to negative 11 joules per nucleus. So in terms of a more convenient energy unit, we use a million electrovolts. And so we just convert that. It becomes negative 128 times 10 raised to 2 million electron volts per nucleus. Then you can calculate the value of the change in E per nucleon by dividing by A. So it becomes negative 7.98 millielectron volts per nucleon. So this is basically the binding energy. And so it's the energy required to decompose this nucleus into its components. And the positive sign for the change in energy per nucleon for oxygen 16, it's positive because energy is required. So if you notice in this graph for the binding energy, okay, notice how the most stable is actually at the top of the curve. So you have oxygen 16, it's the most stable, it's pretty stable, but the most stable here is iron 56. Correct, the iron 56. Okay, right, now let's do nuclear binding energy part 2. Calculate the binding energy per nucleon for the helium nucleus. So you have the mass of the helium atom plus 2 Me is 4.0026, and you have the masses of two protons is 1.0078. So you have to learn how to account for the electron mass. Now, you're going to find the corresponding energy change with delta E is equal to delta M C squared. So you have this one, which is negative 0.034 U over nucleus. And then you multiply that by 1.66 times 10 raised to negative 27 kg per unit, becoming 5.04 times 10 raised to negative 29. So then you notice that a helium nucleus is synthesized from two protons and two neutrons. We see that. Oh, sorry, it's out of order. Okay, so this one's supposed to be first. Right. This one's supposed to be first, and then this is next after that. And then you multiply it and plug it into the equation as 4.54 times 10 raised to negative 12 joules per nucleus. Okay? So we convert that to MeV, and then we find the binding energy per nucleon. Now we have nuclear fission and nuclear fusion. So what's the difference? So nuclear fusion actually combines two light nuclei to form a heavier, more stable nucleus, while nuclear fission, right? It splits a heavy nucleus with two nuclei with smaller mass numbers. So both fusion and fission actually produce stable nucleids and thus are exothermic. So this is your mass number, this is the binding energy per nucleon, and then this is nuclear fusion. So again, it's an exothermic reaction, it releases energy. Same thing for fission, right? It releases energy, it separates. So nuclear fission was actually discovered in the late 1930s when uranium-235 nuclides were bombarded with neutrons and they were split into lighter elements. Okay, so the neutrons are produced in the fission reactions of uranium-235 and you produce a chain reaction. So for a self-sustaining fission process, at least one neutron from each fission event must go on to split into another nucleus. So subcritical reactions, when the process dies out after one fission event. A critical reaction occurs if exactly one neutron from each fission causes another fission event, while a supercritical reaction happens when there is a violent explosion. So, more than one neutron from each fission event causes another fission event, and it rapidly escalates. Now, this nuclear fission was actually used in the Manhattan Project, which was carried out by the US during World War II. The Manhattan Project was carried out by the United States, and they basically built a bomb based on the principles of nuclear fission. So this is actually the basis for the bombs that were released on Hiroshima and Nagasaki. And so they use subcritical masses of fissionable material to form a supercritical mass. That's why the effects were very devastating. So we also use the same principle right now in nuclear reactors. So what happens in nuclear power plants is fission. So the reactors were designed in which controlled fission can occur, and the resulting energy is used to heat water to produce steam to run turbine generators. So you have uranium oxide or refined uranium, and you place it in the cylinder. So uranium has been enriched to have approximately 3% uranium 235, which is very different from the naturally occurring uranium because natural uranium only contains 0.7%. This is housed in cylinders. And what happens is that the moderator surrounds the cylinders to slow down the neutrons so that the uranium fuel can capture them more efficiently. And you also have something called control rods of neutron absorbing material. And they're used to regulate the power level for the reactor. So the reactor is designed so that the malfunction can occur, and the control rods are automatically inserted into the core to stop the reaction. So the water is circulated through the core to extract the heat generated by the energy of fission, and then the energy can then be passed on via a heat exchanger to water in the turbine system. Now the problem is that there is still controversy regarding nuclear reactors because of the failure of the cooling system can lead to temperatures high enough to actually melt the core. What they're trying to do is they're trying to build housing the core must be designed to contain the core even if meltdown occurs. So there is controversy surrounding the efficiency of safety systems in nuclear power plants, particularly what happened to Three Mile Island in Pennsylvania and in Chernobyl, Ukraine in 1986. So pictured is Chernobyl. I have something here called breeder reactors, wherein it's a way to solve the potential problem of the depletion of uranium 235. Okay, so one problem with nuclear energy is because of uranium 235. They believe that if we continue to use it, it will be depleted. So, how do you solve that problem? Remember, we have something called the decay series. I remember you've seen nuclear reactions that continue to occur. So, basically, what you want is a breeder reaction. So, fissional fuels are produced when the reactor runs. So, natural uranium 238 is changed to fissionable plutonium 239. And then what happens is that in the reactor, there's an absorption of a neutron and the production of beta particles. And then the excess neutrons are absorbed by uranium 238 to produce plutonium 239. Then you separate plutonium 239 and then it's used to fuel another reactor. So the reactor breeds nuclear fuel as it operates. So this current technology is actually being used in France. However, in the United States, they have reservations on using this, and to my knowledge, they aren't moving forward with it yet because plutonium actually flames in contact with air and is toxic. Okay. Now, where do we actually use nuclear fusion? So this actually occurs in our sun, where large quantities of energy are produced by the fusion of two light nuclei. So stars produce their energy through nuclear fusion, and our sun gives off energy from the fusion of protons to form helium. Okay. And the thing about fusion, again, you have a positively charged nucleus and a positive particle. So you need a lot of energy for them to react. Okay. So the thing about fusion is that unlike uranium 235, which is heavy and can be depleted, you have light nuclides such as deuterium, you have hydrogen, you have the proton, and it can serve as fuel in fusion reactors. The problem is you need high temperatures to initiate fusion, and they're only effective at very small differences. They must be shot at each other speeds high enough to overcome that electrostatic repulsion. So there are two possible systems that we can use to produce the extremely high temperatures required. Either we use high powered lasers or heating via electrical currents. Now let's touch on the effects of radiation. Now, radiation damage is actually quite scary. So, radioactive elements, as we know, is what happened with Chernobyl, Three Mile Island. They are potentially hazardous. So, there's different types of radioactive damage. One is somatic, one is genetic. So, somatic damage is damage to the organism itself, and it results in sickness or death. Genetic damage is damage to the genetic machinery, and it produces malfunctions in the offspring of the organism. So there are four factors affecting a particular source of radiation. First is the energy, the penetrating ability, the ionizing ability, and the chemical properties. For the energy of radiation, the higher the energy content, the more damage it can cause. So it's actually measured in rads, or radiation absorbed dose. And one rad is 10 raised to negative 2 joules of energy deposited. You also have to think about the penetrating ability of the radiation. How does it go into our skin? Right? So particles and rays are produced in radioactive processes, and they vary in their abilities to penetrate human tissue. So gamma rays are highly penetrating. Beta particles can penetrate approximately 1 cm. Alpha particles are stopped by the skin. Okay. You also have the ionizing ability of the radiation. So gamma rays can penetrate, but they only cause occasional ionization. Alpha particles are effective at causing ionization, right? So if you ingest something like plutonium, it's very damaging. Fourth are the chemical properties of the radiation source. So when a radioactive nuclide is ingested, the effectiveness in causing damage depends on its residence time. Krypton 36 and strontium 90 are beta particle producers. However, the residence time of krypton 36 is actually not that long. it's chemically inert as well. However, strontium is chemically similar to calcium, and once you ingest it, it can cause leukemia and bone cancer. So you have something called REM, which is the rodent equivalent of man. It's different from REM sleep. So number of REMs is equal to the number of RADs times RBE. And RBE represents the relative effectiveness of the radiation, okay, which causes biological damage. So this is the end of our discussion for nuclear chemistry. All right, I'll good luck with your quiz 3 next week. Sorry, quiz 2 next week, and good luck with quiz 3 afterwards. So I hope that you guys are reviewing and studying, and have a good day. Thank you.